Hi class, today we are learning about the quotient rule. So the quotient rule is going to be dealing with taking derivatives of rational functions. So in other words, functions that are written as a quotient of two other functions. So up until now, when we've gotten something like this, we've been able to actually use the product rule to differentiate. So in order to use the product rule, though, you have to first rewrite this function as a product of two functions as opposed to a quotient of two functions. So that would be if we left 2x plus 7, obviously the same, but this denominator, instead of making it division, we make it multiplication. And then we raise it to the power of -1 to indicate that it would go underneath. So now that we've rewritten this as a product of two functions, we can differentiate it using the product rule. So remember, the product rule has us taking the derivative of the first function and then leaving the second function the same, and then adding, leaving the first function the same, and now taking the derivative of the second one. So this is where it becomes a bit more difficult because there's a lot to remember here. We've got to bring down the -1, leave 3x squared, take 1 away from this exponent, so -2, and then multiply by the derivative of what's inside the bracket. So now this is what I like to call the raw derivative, but it's not very useful in this form, so then we would still have to go and do a lot of simplifying, which is kind of what's a pain here. So this would be 2 over 3x squared, and then this would become so then notice there's a lot of negatives here. So instead of doing the plus there, actually, because there's this -1, that would all become negative. So I'm going to say minus 2 times 6 is 12, so 12x plus 42 all over 3x squared. So 3x squared. So it's subtracting this whole thing. So now we don't really like this, right? We want to get a common denominator. So the common denominator is going to be 3x squared all squared. So this already has one 3x squared, so it needs one more. So we get 2 times 3x squared, and then minus 12x minus 42 all over 9x to the power 4, which is just 3x squared all squared. And so when we simplify this fully, we get, this should have been squared here. This 2x and the 6x, that should have been 12x squared, there we go. So, and then this should have been 42x. There we go. I'm sure you guys all noticed that already, right? You all are paying very close attention. So we get minus 6x squared minus 42x divided by 9x to the power 4, which gives us, and now we can actually common factor out a 3 from the top and a 3 from the bottom. So reduce it to minus 2x minus 14 over 3x to the power 3. So basically, I just common factored a 3x and reduced it that way. So the derivative part of this isn't really what's super complicated as long as you understand this part here. What's complicated is all this simplification, okay? And you should have the algebra skills to do it, but the question is there a way of creating a special rule that we always use for quotients instead of having to always use the product rule and then do a whole bunch of fancy-dancy simplifying? So let's actually go ahead and find out what this quotient rule would be. And we can do this by just taking the derivative of any any general quotient as a product and seeing what the pattern is that always occurs. Okay, so this is what the quotient rule will end up being, okay? We'll get there, but let's prove why it's actually true. So again, our method of proof, which is what I really need you to understand here, our method of proof is that we are going to rewrite our function as a product instead of as a quotient. So notice how I'm putting g at x in square brackets. The reason I'm doing that is to really indicate that this entire function is to the power of -1 instead of just this x, okay? The x, remember, that's the input into the function. So if just that was brought to the -1, then that would just change the input instead of the output. So that's why the square brackets are necessary and important. Okay, you're taking the output of the function to the power -1, not the input. Okay, so now let me go ahead and actually just take the derivative of this as I would. So you take the derivative of the first, okay, and then you leave the second guy exactly as he is already written. Okay, and then you add, keeping the second function as it's written, but now we're taking the derivative of this guy. So that involves bringing down the -1. Now g at x is left the same, but raised to the -2, and then we have to multiply that by g prime at x, by the derivative of g prime at x. So then we go about simplifying it. So this becomes f prime at x over g at x. Okay, and now look at all this stuff that happens here. It's always this minus here, so we can subtract f at x times g prime at x all over g at x all squared. Okay, so now the process is getting a common denominator. So to get that, we have to multiply our first quotient here by g at x over g at x. So you get f prime at x times g at x, subtract f at x times g prime at x, and then it's all over g at x squared, and we're done. So if you had a problem understanding any of those lines, go back and try the number example again and see, make sure you understand that. So then if you understand that, then this should be straightforward. Okay, so this is the quotient rule. It's not anything super magical. It's not like it's a super simple rule or anything, but it's something that you can memorize and use over and over. So let's remember that f at x is referring to the function on the top, and g at x is referring to the function on the bottom. So I always think about this actually as the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So you might want to remember that. So I always just think of it as, so if y equals top over bottom, then y prime is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that is literally has been in my head since 2002, 2003, when I took, that's when I took it, when I initially took calculus when I was in grade 12. So that's just something you will learn to do. So let's actually differentiate this using the quotient rule. Okay. So we have our top and we have our bottom. So when I'm talking about top, I mean the whole thing 3x minus 4, and the bottom is x squared plus 5. So we start with the proper notation, h prime at x. So we do the bottom, x squared plus 5, times the derivative of the top, 3, minus the top, 3x minus 4, times the derivative of the bottom, which is 2x, all over the bottom squared. Okay, now what's good is that I'm going to simplify this, but usually you can just leave the bottom squared like this unless you can reduce it somehow, but you don't actually have to expand that square. That's already in the simplified form. You don't want to overcomplicate it by expanding that when you don't need to. So what you really want to be careful with when simplifying quotient rule questions is this subtraction. It really messes people up. That means you're subtracting this entire side. So often I like to kind of think about square brackets around here, figure out what's in there first, and then subtract it just so I don't make any mistakes. I'm better at it now because I've done it so often, but you might want to consider doing that. So you get 3x squared plus 15. Okay, so 3x times 2x is 6x squared, so minus 6x squared. And then negative 4 times 2x is minus 8x, but I'm subtracting it, so it becomes plus 8x. Okay, all over the bottom squared, which again, you can leave as it is. And now you just collect like terms. So you get minus 3x squared plus 8x plus 15 all over x squared plus 5 squared. Obviously that should be centered. I just ran out of room. Okay, so I have a practice question for you now, and I want you to pause the video and try this. So notice that there's two parts. So I want you to actually differentiate this using the quotient rule, and then verify it by doing it the product rule way to see that you get the same thing. Okay, so what you should get in both cases is, once simplified, minus 5x squared plus 40x minus 1 all over 4 minus x all squared. So just be careful with your negatives as you're doing this. I know I had to really think about that because there's like a negative, I think there's like 3 negatives in a row. You got to think what that does. But I really do want you to pause right now and try this because then we go into a little bit more complicated stuff. Okay, so now we're going to determine the equation of the tangent to this at x equals 0. So this rational function, I graphed it for you already. This is what it looks like. So 2x over x squared plus 1 is this green function. So the question is asking us, determine the equation of the tangent at x equals 0. So you can see x equals 0. It's right here. So the equation of this tangent, you can see it's going to have a positive slope. Okay, the derivative here will be positive because the tangent here would be sloping up. Okay, so we can actually go ahead and find that now since we know the quotient rule. So the equation of a tangent, that's just a line. So remember, it will be in the form y equals mx plus b. And remember now, it's our job to find the m, which is just the derivative at x equals 0. Okay, because that's the slope of the tangent, so that will give us the slope. Okay, just want to remind yourself what it is we're actually doing. So dy dx is equal to, so the bottom, x squared plus 1, squared, times the derivative of the top, 2, minus the top, 2x, times the derivative of the bottom, 2x, all over the bottom squared. Okay, so you can simplify this if you want to, but because we're just actually finding a number, we're just trying to find the slope at x equals 0, you can just throw in 0 now and see what you get instead of going through the work to simplify it. You can simplify it, but it's not necessary, if that makes sense. So you get 0 plus 1 times 2 minus 0 times 0 all over 0 plus 1 squared. So that will give us 2. So that means the slope of the tangent is 2. Now we can find at x equals 0, y is also equal to 0. Okay, if I throw 0 into this function, I get 0, 0. So that is the point of tangency. So it's quite clear then that my answer to this question is y equals 2x. Okay, because the y-intercept is 0. That's the equation. So if you go back to the graph, you can see here y equals 2x. That is the tangent. Okay, also if you're in GeoGebra, you can put the tangent of 0 at f, and it gives you that it's 2x. Okay, so you can do that in GeoGebra as well. So there you go. That is that question. Okay, let's move on to the next example. Okay, determine the coordinates of the graph. Determine the coordinates of each point on this graph where the tangent is horizontal. Draw a diagram to represent this situation. Okay, so I actually, first of all, went to GeoGebra to graph this function. So it looks like this. Okay, it's kind of a strange rational function. Notice that it is only, sorry, just a minute. The domain of this function is x is greater than 0, based on the fact that it's the square root of x on the denominator. So this only exists in quadrant 1. And you'll notice too that it increases over time. Okay, so there's a vertical asymptote here at 0. And so the question is asking, where is this guy? Where does he have a tangent that is horizontal? So in other words, where is the derivative equal to 0? Where is the slope of the tangent 0? So you can see visually, like here would be negative, 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 and then turning to positive. So it looks like 4 might be the right answer. Okay. Now, it's cool because in GeoGebra, you can actually solve f prime equals 0. You can actually write that in, and it tells me that the answer is x equals 4. Okay, so GeoGebra will actually tell me that. You can also see I put y is equal to f at x. So this is actually the a picture of the derivative function. Okay, so you can see that it crosses the x-axis at 4. So the solution will be 4. We can see that visually. Notice also if we put y equals 8, you get it there where it's touching. Okay, you can also write tangent, tangent at 4 on the function f. Okay, you'll see it's y equals 8, which is a horizontal line. So all of these different ways of using technology verify what we're going to do now algebraically. Okay, so when I say draw a diagram, I'm going to say showing that stuff on GeoGebra is equivalent. So you can make some visuals on your note here that represent what we did there. So again, the tangent is horizontal where the derivative is equal to 0. The derivative is the slope of the tangent. We want it to be equal to 0. So first we need to actually find the derivative. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom. So remember that this is x to the 1/2. So that's 1/2 x to the negative 1/2 times 1. But we're going to have to deal with that later. All over the bottom square. So the root of x squared is just x. So sorry, there shouldn't be. It's just x, okay? So now we need to do a little bit of work to make this look nicer. So this is just, we would write it as 2 root x, but what are we going to do over here? Well, this times 1/2 is pretty obvious. I get x plus 4. But what do I do with this? So remember, x to the negative 1/2 is the same thing as this all being over root x. Okay? And so now this is all over x. So how do I simplify that to look nicer? Well, first of all, on the quote-unquote on the top, I should get a common denominator of root x. So when I do that, I multiply this by root x over root x. So 2 times root x is just x minus 4 all over root x. And then all of that's being divided by x. So instead of writing it as division, I'll write it as times 1 over x, just so I don't have fractions on fractions. It looks gross. Okay, so what did I do here? So if you are confused, just take a moment to pause this and look at it. I got a common denominator on this top. That's all I did, and distributed this negative. That's all I did over here. And then instead of writing divided by x, I wrote it as multiplying by 1 over x. If this confuses you, make a big star. I will explain it to you in person in class. Okay, so at this point now you just simplify to x minus 4 divided by x root x. And that is the derivative function. Okay, this is the derivative function. So where is this guy equal to 0 is what we need to solve now. So I'll just kind of do a different color over here. So now I want to set x minus 4 over x root x equal to 0. And so when I solve that, you can just cross multiply. So then I just get x minus 4 equals 0. So x is equal to 4. Okay. Notice that it does say the coordinate of each point. So because it's not enough for me to now just say x equals 4, it's asked for the coordinate. So to find the y value, I put 4 into the original function, okay, not the derivative, and I get 8. So 4, 8 is the coordinate. That gives a horizontal tangent. Okay, one last question. And this is a contextual question. So let's wrap our head around what this function is actually saying and also its meaning. So the meaning of the derivative, sorry. So it does say practice here. So I would encourage you as I go through this to try to pause and do sections on your own and then turn the video back on to see if you were right. But I am going to go through this because it is a word problem. So this grocery store determines that after T hours on the job, a new cashier can scan this many items per minute. So before we even go on to the derivative, let's take a look at what this function, what's going on here. So 20 minus this weird thing going on. So notice if I go and I graph just this function on GeoGebra, so let's not look at the derivative yet. First of all, I can ignore it for any values less than 0 because we're T is in hours, so we're only spending positive hours on the job. So notice here that the intercept is 10. So that means at 0 hours, when they just start a new cashier, they can scan 10 items per minute. Okay, and notice that for the longer they work, the amount of items that they can scan per minute increases and increases and increases. So for example, at 4 hours, now they can scan, it looks like about 14 items per minute. After 10 hours, about 17 items per minute, and it looks like it's reaching a horizontal asymptote of 20, which is what is happening. Because if you look at this part of the function approaches 0, so this entire function will approach 20. So, I mean, in real life, it doesn't make sense that you would get closer and closer to 20 items a minute without getting there. Really, this is just a way of representing a function where probably the maximum amount they're able to scan a minute is 20. Okay, so you have to think about mathematically the difference between what's really going on and how useful the model is in terms of the actual math. So sometimes those two things are right together, they coincide, but in cases like this, you kind of have to use some logic as well as the math to interpret what's happening. So it says find the derivative and explain what it means. Okay, so let's just go and actually find the derivative first, and then we'll talk about what it means. So n prime at t. So we think about this as something plus something. So the derivative of 20 is just 0, so we can write it as 0. But then we have to go through and actually take the derivative of this second part. So what is, what was I going to say? So what is the derivative of this? Well, this is a quotient. So we take the bottom and multiply it by the derivative of the top, which is actually just 0. So that's cool because a bunch of that's going to go away then. And then we subtract the top times the derivative of the bottom. So here we have to do this whole half bracket 9 plus t squared to the negative a half, and then multiply it by 2t because that is the derivative of what's inside there. So now this is all over 9 plus t squared. So at least square roots square nicely. Okay, so this just goes away, but now we have the job of simplifying this guy. So what does that look like? Well, 30 times a half is 15, but then times 2 again. So I get 30t. And actually, this whole thing is negative out here because of this subtraction. So that's why this ends up being positive. You get 30t over 9 plus t squared to the half, and then times 1 over 9 plus t squared. So if I multiply this together using my exponent laws, I get 30t over 9 plus t squared to the power 3 over 2. Okay, I just added the exponents. This is technically to the power 1. So I just add the exponents to get this. So this is my derivative function. What on earth does it mean? So basically, this is the number of items per minute. So how is their rate of scanning changing? Okay, so for instance, if they're able to scan 10 items and the derivative is 2, then that means they're improving by 2 items per minute every minute. So they'll be getting up to 12 items per minute. Okay, if the derivative was negative, that would mean that their performance was decreasing, so that they were actually going down in how many items per minute they could scan. Okay, so it's important that you understand that. So if I actually graph the derivative here, you can see that there's a very high thing at first, so that my derivative goes up kind of quickly. And that makes sense because they're, as they're learning, as they're on the job, their rate of improvement gets quick quickly because they're learning. Okay, and then notice though my derivative stays positive, but the amount at which they're changing is lessening. So they're getting a lot better quickly, but then they're still getting better, but just not as at quite quick of a rate. So notice if we find, for instance, f prime at 4 is 0.96. So that means at 4 hours of work, right at that point, they're improving at about 9.96 items per minute every minute. Okay, so that's what the derivative means. Now, according to this model, does the cashier ever stop improving? Why or why not? No, according to this model, they actually don't stop improving. So we can take a look at that in 2 ways. First of all, we're getting closer and closer to 20 items per minute on the original function, but then you can see the derivative is getting closer and closer to 0, but won't actually quite ever get there. So that means they're always slightly improving, but it's always under 20 items per minute. So in reality, I mean, there probably is a max that they're going to hit. You can only go so fast as a cashier. But technically, according to the model, no, they don't stop improving. So guys, that's the quotient rule. Thanks for watching. Hope you learned lots.